Welcome to today's Explainer. Look at the headlines, talk to your peers, or honestly just scroll through the internet for 5 minutes, and you're going to feel it. This massive, almost paralyzing anxiety about AI. The whole narrative paints artificial intelligence as this dark, mysterious, uncontrollable entity, a giant black box that we're blindly pouring power into without actually knowing what's going on inside. And hey, it's a completely natural fear. But today, we're moving past the anxiety. We're going to demystify the whole thing by looking at the actual, concrete engineering blueprint for AI interpretability.
So, we got to start with the core question driving that existential doomer narrative you see literally everywhere. Are we building an uncontrollable black box? Is AI just going to experience these arbitrary, unchecked leaps in capability until it's completely out of our hands? It's a totally valid apprehension, for sure. But to really understand where AI is heading, we need to systematically dismantle this idea by looking at the hard science and the strict mathematical constraints that actually govern these systems.
Okay, let's dive into this. On the one hand, you've got the doomer narrative. It's the classic sci-fi fear, right? That AI is this inscrutable, magical black box making arbitrary leaps in logic that human brains can never comprehend. But contrast that with the reality of rigorous control. Modern AI development isn't magic. It's blueprint-level engineering. We're talking about circuit-level debugging, deeply mapped pathways, and strict physical constraints. AI isn't some uncontrollable ghost in the machine. It is a highly complex but ultimately readable piece of software. To show you exactly how this works, here's the master schematic for today's explainer. First, we'll unpack the black box myth. Second, mechanistic interpretability explained. Third, enter sparse autoencoders. Fourth, debugging AI personalities. And finally, we'll ground it all in AI's mathematical constraints. Section 1. The black box myth. Let's pop the hood on AI. So why does AI look like a black box to us in the first place? Well, it boils down to a concept called superposition. To be incredibly efficient, neural networks compress multiple, entirely distinct concepts into single activations. Imagine trying to read a map where 20 different cities are printed literally right on top of each other. It's a mess, right? It's incredibly entangled. That superposition is exactly why it's historically been so tough to audit how an AI reaches a specific conclusion. But hold that thought, because it sets up our next core concept perfectly. Section 2. Mechanistic Interpretability Explained. Engineering the AI brain. All right, here's the specific vocabulary you need to know. Mechanistic interpretability. This is basically the science of treating neural networks as physical objects. Instead of treating the AI like some magical oracle on a mountain, researchers are reverse engineering its internal weights and activations into understandable, readable algorithms. And why does this matter to us? Because it means we aren't at the mercy of algorithms we can't understand. Researchers are literally auditing the inner workings of the AI's brain exactly as if it were a traditional, everyday software program. Section 3. Enter Sparse Autoencoders, the ultimate debugging tool. Let's talk about a specific tool pioneered by labs like Anthropic and DeepMind, Sparse Autoencoders, or SAEs. These are algorithms designed to take those densely entangled neural activations we just talked about and factorize them into a sparse basis of disentangled features. Okay, let's translate that dense math into something tangible. Think of SAEs like a prism. They take this highly compressed, tangled beam of AI thought and cleanly separate it out into distinct, isolated, readable circuit pathways. It's a real game changer. Here are the mechanical steps of how we actually go from a mysterious black box to a clean schematic. Step 1. We take those compressed, entangled activations, the superposition. Step 2. We factorize them into disentangled features using our sparse autoencoders. And Step 3. We isolate specific circuit pathways. This is absolutely crucial because it means we have literally mapped the AI's thought process step by step. No more guesswork. Section 4. Debugging AI personalities. Editing the persona vectors.
Now, what's incredibly interesting here is how we can isolate and directly edit what researchers call persona vectors. Take sycophancy, for example. That's when the AI acts like a desperate corporate yes man, just blindly agreeing with your terrible ideas to please you. Or hallucination, where it literally just makes things up. Because we can map these specific behavioral circuits using sparse autoencoders, researchers can monitor them and physically edit these vectors to prevent undesirable behaviors entirely. The big takeaway for you here? We have the steering wheel. We can debug these models long before they ever hit the public.
Section 5. AI's mathematical constraints. Hitting the hard walls of reality.
Let's look at the foundational math for a second. Mathematical uncomputability.
Without getting lost in complex proofs, the math guarantees one simple, unavoidable fact. No computing engine can ever be perfectly error-free. Because of unsolvable logic loops, there are infinite ways for any model to fail. This proves that just pumping more compute power into a machine won't magically produce an infallible, godlike AI. The math simply doesn't allow it. It is a hard boundary. So, the crucial point is this next limitation, the chinchilla limit. AI models are facing a massive data wall. Optimal pre-training requires scaling parameters and training data in a near-proportional relationship. But here's the catch. High-quality, human-generated text is rapidly approaching exhaustion. Let that sink in for a second. We are fundamentally running out of raw human words to feed these massive systems to keep scaling them up endlessly. It's wild to think about.
Beyond just the data, there are hard physical realities anchoring AI against infinite growth. As the parameter scale grows, we hit wall 1, chip manufacturing limits. We can physically only build so many advanced semiconductors. Then comes wall 2, power availability constraints. These data centers require massive thermodynamic output, and honestly, our energy grid has limits. And finally, wall 3, decoding limits. There is quite literally a physical speed limit to how fast these models can generate words one after the other. The laws of physics themselves act as an anchor here.
And this brilliantly illustrates the massive industry shift we're seeing right now. Because of all these hard mathematical and physical constraints, the industry is moving away from brute force scaling. Instead of blindly building bigger black boxes, the focus is shifting to highly efficient training, models that retrieve specific facts, and structured pipelines. Constraints are basically forcing the industry to build smarter, more auditable, and much more efficient systems.
Let's wrap this up with a quote that perfectly summarizes our entire journey today. We don't need to guess what an AI is thinking. We can map, isolate, and debug its pathways. AI is a tool, and it's governed by strict physical limits, mathematical laws, and readable algorithms. It is not an uncontrollable magic box, and we are developing the exact tools needed to ensure it stays that way.
Which leaves us with one final, incredibly exciting thought. Now that we have the blueprint to actually read the AI's mind, what pathways will we choose to map next? The possibilities for making these systems safer and more aligned with our needs are just endless. Thank you for joining me for this explainer. Keep questioning, keep discovering, and I'll catch you next time.